Hey, how's it going? So we're in Algebra 1, Unit 4, Modeling and Analyzing Quadratic Functions. And for this module, we'll be looking at adding and subtracting polynomials. All right, so for every addition problem that we're going to look at, we're going to also look at a subtraction of the same polynomial so you can start to compare and contrast them. All right, so let's go ahead and first look here. We're going to add these two polynomials, 4x squared minus 7x plus 10 plus 2x squared plus 4x minus 8. All right. So then now when it comes to adding polynomials, a lot of times you'll hear it written as or stated as combining like terms because that's literally kind of what it is. When they say like terms, they're saying terms with the same base. So if I look here, 4x squared and 2x squared have the same base. The base is x squared. Negative 7x and 4x have the same base, which is x. 10 and negative 8 have the same base, which is x to the 0 power, which is the same thing as just a constant with no x there. All right. But that's just the math behind it, I would say. All right. So then now, when you combine like terms, I would say go ahead and stack them. Stack the like terms. 4x squared and 2x squared, negative 7x and 4x, and then 10 and negative 8. Then you can add straight down. But notice when I add straight down, I don't add the exponents. That's only when you multiply polynomials, and you subtract the exponents when you divide polynomials. But because when you're adding and subtracting polynomials, you're simply just adding and subtracting the coefficients and bringing the base with it. So 4 plus 2 gives me 6. Bring the x squared down. Negative 7x plus 4x gives me negative 3x. And 10 minus 8 gives me a positive 2. All right, so now we're going to look at that same polynomial. Instead of adding, we're going to subtract. We're actually going to do it very similar. Because there's no number in front of the 4x squared minus 7x plus 10, we just bring that down as is. So we don't necessarily change that at all. But now when it comes to this negative, this is like having a negative 1. And this is like having negative 1, and you have to multiply that by every term inside. What that does is it changes all those signs. So negative 1 times 2 is negative 2. Negative 1 times 4 is negative 4. Negative 1 times negative 8 is a positive 8. So then now from here, I do the same thing I did up here, but now all these signs have changed because I distributed negative 1. Now when I stack them with the like terms, instead of having 4 and positive 2, I have 4 and negative 2. Instead of having negative 7 and a positive 4, I have negative 7 and a negative 4. And instead of having 10 and a negative 8, I have 10 and a positive 8. So when I add straight down, I get 2x squared minus 11x plus 18. So now let's go ahead and look at our next two examples. So we'll do the same thing that we did in the previous two examples. When you add, just go ahead and stack your like terms. We got 13x squared and negative 5x squared. We have 4x and a negative 1x. So if you have a negative x, that's understood to be a 1 right there. And you have a negative 7 and a positive 2. Go ahead and stack them. And then from here, you add straight down, but you just bring the base with it. So 13 plus negative 5, or 13 minus 5, you get 8x squared. 4 minus 1 is 3. And then negative 7 plus 2 is negative 5. Now let's look at our subtraction example. So 13x squared plus 4x minus 7 is not adjusted. It doesn't have to get changed because there's no, or manipulated because there's no variable or sign in front of that polynomial. All right. But this minus sign tells us that I have to change the signs over here though. So I'll have 13x squared, but now instead of having a negative 5x squared, I'll have a positive 5x squared. Instead of having a negative 1x, I'll have a positive 1x. Instead of having a 2, I'll have a negative 2. Because as a reminder, we distribute the negative 1 throughout. All right, but when you distribute that negative 1 throughout, don't just bring the negative down. You got to bring whatever the sign of this term down. That sign is now a positive 5x squared. That's why it's a plus 5x squared here. So now let's go ahead and stack them. From here, you got 13 plus 5 gives you 18x squared. And then you have 4 plus 1 gives you 5x. And then negative 7 minus 2 gives you negative 9. So this is your final result. Now what I want to do is show you how you could check your work when it comes to adding and subtracting polynomials. Your original problem and your final result are going to create the same function. What do I mean by that? Look here, this is the original problem, right? 13x squared plus 4x minus 7 plus negative 5x squared minus x plus 2. If I look at my end result, look how the end result gives me the same graph. So if you ever get confused, you can always be able to double check your work by actually typing this in and making sure the graph matches. Very similar to how we looked at simplifying radicals. When you look at the original problem and the end result, they should match, all right? So now let's go ahead and check the other example just to show you that it works for subtraction as well. So if I put the minus sign there, and then all of a sudden we had, what was it, 18x squared plus 5x minus 9. And as you can see here, it gives you the same graph. That's how you will be able to know that you're correct. All right, just a quick way to how to check your work, just to confirm that your answer is correct. All right, so with that being said, let's go ahead and look at some more examples. So now we have 2x squared minus 5 plus 7x squared minus 2x plus 1. This problem I'll say is a little tricky because notice that when you want to stack these, you have a like term of 2x squared and 7x squared, and then you have a like term of negative 5 and a positive 1. You only have one x term. So when you stack them, make sure you stack them correctly. So then now I can just simply add 2 plus 7 and get 9x squared. There is no other x term, so I just bring that negative 2x down. And then negative 5 plus 1 gives me negative 4. So that's my end result. So if I subtract, the 2x squared minus 5 is the same. You keep that as is. And then now that 7x squared is going to be a negative 7x squared. That negative 2x is not going to be a positive 2x. And that 1 is not going to be a negative 1 because we distributed negative 1 throughout. Now when you stack, it'll be very similar to our last example up here. And then when you add down, you get 2 minus 7 and get negative 5x squared, 2x. And then from here, we get negative 6. And as a reminder, when you type in your original problem and your end result, you should get the same exact function. So when you graph it, it should match. Same thing with the subtraction. The original problem and your answer should give you the same exact function. All right. So then this will be our last example, two examples before we start to look at it in context. All right. So if we add, we're adding polynomials. So we have negative x squared plus 2x minus 3. And then so now when we stack them, the negative 4x is going to go under 2x. All right. The negative 5 goes under the negative 3. As you can see here. All right. Make sure you have like terms are there. All right. So then from here, you add straight down, you get negative x squared. 2 minus 4 is negative 2x. And then negative 3 minus 5 is a negative 8. All right. And one thing I did not discuss so far, but I kind of want to discuss it, is you can't necessarily type the addition and subtraction into Desmos. So if you wanted to type in 2x minus 4x, it's not going to give you the negative 2x, all right? So you would have to type it in without the x's or the x squares there, and then you just have to know to bring the base with it, all right? So then now let's go ahead and look at subtraction. So then we're going to change both of those signs. So then that's a positive 4x now and then positive 5 now. Now when I stack them, the negative x squared will still come down as is because there's no other term, like term. 4 plus 2 gives me 6x, and then negative 3 plus 5 gives me a positive 2. All right, so now what if you're looking at it in context? If I want to find the perimeter here, in order to find the perimeter of a figure, you're going to add up all the sides. So then you would add up 2n plus 1, 2n plus 5, plus n plus 5. Add up all three of those sides. Same thing, let's go ahead and stack them. So then now I have 2n plus 2n plus 1n, and I get 2 plus 2 plus 1 is 5. So I get 5n, and then 1 plus 5 is 6, plus 5 is 11. And that's your final result. Now let's go ahead and look at our next example. So here, this is a rectangle. So when you see these two dashes here, this tells you that 6t plus 5 is the measurement of this side, and it's also the measurement of this side. These two dashes tell you that these two are equivalent as well, which means that this side is 2t plus 1, and so is this side. So if I'm looking for the perimeter, I'm going to add up all those sides. So that's 6t plus 5 plus 6t plus 5, and 2t plus 1 plus 2t plus 1. And then, just like we did in the last problem, go ahead and stack them. So 6t plus 5, 6t plus 5, 2t plus 1, 2t plus 1. And then that will give you the result of 16t plus 12. So that's the perimeter of this figure. All right, so now let's go ahead and look at our last problem. So what happens if you have a figure that looks like this? The fact that you have that one dash, you have it everywhere, that tells you that this is going to be a square. That means that all four of these sides are equivalent measurements. So if I'm looking for the perimeter, I need to add 7r plus 2 4 times. 7r plus 2 plus 7r plus 2 plus 7r plus 2 and 7 plus 7r plus 2. You get the gist. So then now go ahead and stack them all up. So you stack all four of them together. Now add up the left column, 7r's. They all have like terms. And then 7 plus 7 plus 7 plus 7 is 28. So it's 28r. 2 plus 2 plus 2 plus 2 is 8. So that's 28r plus 8 is the perimeter of this square here. All right. So now with that being said, it is time to practice. Questions, concerns, feel free to let me know.